start. So welcome everybody to the webinar of today. The speaker of today is Francois Schmidt, and he's going to talk about a quadratic Reynolds stress development for turbulent Kolmogorov flow and comparison with the channel flow in a DNS study. As usual, I introduce the speaker very briefly and then I leave him the floor. So Francois Schmidt has been granted an engineering degree by the École Nationale Supérieure de Technique Avancée, ENSTA, in Paris. In 1993, he defended his PhD in physics at the University of Paris 6. Francois Schmidt is CNRS senior researcher, is directeur de recherche at the Laboratoire d'Océanologie et de Géosciences Bimero in France. He's president of the Scientific Council of the French CNRS ENSU program LEFE since 2021 and head of the French National Network of High-Frequency Coastal Biogeochemical Observation since 2019. He was the PI of the project Marco, Marine and Littoral Research of the Opal Coast, with 5 organisms involved, 8 laboratories and over 200 members from 2015 to 2020 to 2021. His research interest range from oceanography, marine physics, ecology coupling, turbulence, multifactor models, intermittency models, and at viscosity type modeling. So it's with great pleasure that I introduce Francois Schmidt. So Francois, I stop sharing my screen such that you can start sharing yours, and then please feel free to start your presentation. There we go. We see your screen.
So I think it's okay.
Yeah, it's full screen mode. That's perfect. Thanks.
Okay, thanks. So merci pour l'invitation. Thanks for the invitation. So the title is shown here. It's a joint work for the second part of what I'm going to present. It's a joint work with colleagues Wenwei Wu, Lipo Wang from Shanghai, and also Enrico Calzaverini, which is here in the room. So about my lab, so I'm, as you presented, I'm from Laboratoire of Oceanology and Geosciences, which is LOG in Vimereux. We are working in interdisciplinary laboratory, so we are working in geosciences, in marine ecology and in physics, and we are located here in this campus and also mainly in Vimereux, which is in the coast, about 100 kilometers from here. And we have different tutela, and one of them is University of Lille. So that's the outline of my presentation. So my presentation is about Boussinesq modeling in turbulence. So I'm first giving some very shortly some historical remark about it, and then I recall some results that I obtained some time ago about the test of this hypothesis using different type of flows, including direct numerical simulation channel flows. And then I apply it to the turbulent Kolmogorov flow. And I also make some comparisons between channel flow and Kolmogorov flow. So as we know, when we average the Navier-Stokes equation, we obtain the Reynolds stress, which needs to be closed. It means to be expressed using mean quantities of the flow, and the classical closure, which is proposed, is a linear closure, which is called Boussinesq hypothesis. So it's useful. In fact, I think it's always useful to go back to the original sources to see what people have indicated. And this can be found in the website of the French National Library. It's a website called Gallica, where many old papers can be found. And so we can see that in fact the original paper, which is shown here, the memoir was published by Compte Rendu de l'Académie des Sciences in France, in Paris. And before this, in fact, Boussinesq gave a talk in 1972, and this talk was published as a long memoir a bit later, 5 years later. And also there was an essay, a kind of introduction by Saint-Venant, which is called Essai sur la théorie des eaux courantes. And in this original source, we can see, in fact, that Boussinesq was claiming that if we do an average of Navier's, he was calling it Navier equation, not Navier-Stokes. And he was saying that if we make an average of Navier equation, then we still obtain Navier equation, but by replacing the viscosity by something which is variable and a new quantity which is variable. And so Saint-Venant in the introduction said that Boussinesq has solved a desperate enigma, so a desperate enigma. And he really thought that it was an exact representation, because he said, okay, if we average Navier equation, we obtain, as I said, the same equation, but with a variable internal coefficient, which they call epsilon. It was the first introduction of this eddy viscosity. And we can also find the equation in the work of Boussinesq, and we see that it's a tensorial expression. And if we translate this into the present day notations, then we can see that we have the tensorial classical development, which is used now. And also in the same paper, it's interesting also to see that Boussinesq has proposed a mixing length expression for epsilon that he called epsilon, which is eddy viscosity. So it was, in fact, the first mixing length expression several decades before Prandtl. And so this famous true enigma, they thought that Boussinesq has solved. It was even mentioned when in a posthumous speech, when after the death of Boussinesq, so the president of the Academy of Science, which is a mathematician, Émile Picard, made a speech, and he said, okay, since Boussinesq, we know that we can average the Navier equation, but we need to have a variable coefficient. So until the 30s, in fact, it shows that people thought that Boussinesq approach was exact. And also what is interesting is that they're not using turbulence. The word turbulence, they're using different words. In Boussinesq, he's using mouvement tumultueux, théorie des remous, théorie des tourbillons liquides, so I mean liquid eddy agitations. And Reynolds use also some periphrase like sinuous paths, sinuous motions. So the word turbulence was used only in 1887 it was proposed by Lord Kelvin in a paper that can be found here. But in fact, Boussinesq and Reynolds, even in late works, they did not use the word turbulence. So these different historical aspects, I discussed them in these two papers published in Compte Rendu Mécanique in 2007 and 2017. So going back to the second part about the direct test of Boussinesq approximation. So I recall the expression of this approximation, this linear closure. If we use the traceless Reynolds stress tensor, which is called R, then it corresponds to this hypothesis corresponds to alignment between two tensors, and the alignment coefficient is simply 2 nu t. And classically, in the classical models, then this nu t is expressed as other, using, because it's variable, so it's expressed as a function of other variables, like a function of k and epsilon, of k and omega, or of a length scale. And this gives different, a lot of very classical models. The first ones being so for the Prandtl, it was not a turbulence model, but for Kolmogorov 42, it was the first try to make a modeling. And and people also use classically transport equations for K, for epsilon, or for omega in these models. And it's very, there is a big success, in fact, of these models, because the original papers have thousands of citations, and they are really applied in many fields, like in engineering, in meteorology. It's used a lot, and also in oceanography. Almost all ocean models are using this approximation. So it's useful, in fact, to check it. That's what I have done almost 2 decades ago. And so I was interested by, in fact, trying to test it directly. And this can be done by simply making a projection. So it's a tensorial inner product, which is also called Frobenius double dot product. So simply it's AIG, BIG, and so we can normalize by the norm, and we obtain an indicator, and this indicator is giving information about the alignment between the two tensors. It's like the cosine of the angle of the two tensors. If we apply this to R and S, we obtain an indicator, which I introduced in this 2007 paper. So it's corresponds to the alignment between the traceless stress and the mean strain. And this indicator is between -1 and 1. And when it's 1, the hypothesis is valid. And when it's different from 1, the hypothesis is not working anymore, and when it's 0, the hypothesis is a failure. So we can apply this to a different database. First, I applied it to some simpler shear flows, so some boundary layer flow, annular or parallel channel flows, and also quet flows. And for this, in fact, we have only one non-zero component of the mean velocity gradient tensor, and we have only one non-zero non-diagonal component of the stress tensor. So the two tensors are shown here, and we can see directly that, in fact, for the R tensor to be proportional to the other one, we need to have the diagonal, which is 0. So meaning that, in fact, we need to have some isotropy in the normal stresses. And in fact, we see on the right panel, on the right here, that the different normal, this is shown for different databases, DNS databases, and we can see that they all show that it's not isotropic. The U square, V square, and W square are not do not show the same values. So it shows, in fact, that the Boussinesq hypothesis cannot be valid for this flow, but the indicator is a way to quantify this non-validity. So the indicator is shown here, and we see that it's close. It's very close to the wall. This is here, as usual, the distance to the wall in normalized units. In this place, close to the wall, in fact, the viscous stress is dominating. That's why it's 1. And for the rest of the flow is far from 1. We have a plateau very far from the wall. Here, more or less a plateau, and we have a local minimum where the value of the indicator is very small. This was done also for annular channel flow, and for this, in fact, the representation of the channel flow, it's the flow between the two cylinders, which are shown here, and here the walls on the left and the right, and we see here the different normal stresses, and here the indicator. And the indicator is never reaching 1, only in the walls, and it's close to 0, even 0, when corresponding to the values of the mean velocity, very small values of the mean velocity. So it means when the mean velocity shear is very small, then we have a failure, total failure of the hypothesis. This can also be done using experimental data. For this, I have used usually using experimental data, you can obtain the Reynolds stress very easily for each grid point, and the strain can be obtained. In fact, if we have a good grid and if we can make approximation of the gradient, it's what has been done here for this experiment. And so the strain lines are shown here. And the indicator is shown as a color code. And we can see, so it's close to 1 for the red part. And we can see that the red part is only found in a limited region of the flow. And for the rest of the flow, we are quite far from the red color. So globally, this shows that even for weak gradients, in fact, this hypothesis is not working, and even in complex flows, and for simplest flows, and also for complex flows, it doesn't work. So one possibility to go further is to consider nonlinear models, so like a nonlinear constitutive equation, and also it corresponds to nonlinear eddy viscosity models. So for this, we express R as a function of the mean strain tensor and the mean rotation tensor W, and in the mathematical framework of the invariant theory for matrices. So it was proposed in the mathematical literature by Rivlin and Spencer in the 50s and 70s, and after this it was first applied to turbulence by Pope in his paper of 1975, and Pope showed that in fact we need to have 10 a maximum of 10 development of a basis on 10 tensors. And so R can be expressed as a linear combination of these tensors, where the coefficients are expressed from the invariance of the flow. For simple flows, like the flow of the channel flow, the wall, and also the Kolmogorov flow, in fact, it can be shown that we need only 3 terms. So it means we can consider a quadratic model, and for this quadratic model, so in the here, I don't know, actually. Okay, I cannot move this so easily. So in fact, we have the 3 terms. The first one is a linear one. T2 is SW minus WS, and T3 is S square minus its trace. And the coefficient can be obtained, they depend on invariance of the flow, and they also can be obtained as a projection on the tensor basis. So it was proposed first in a paper of Jungen and Gatsky in 98. And then for the channel flow, and also for the Kolmogorov flow, the coefficients are expressed as very simply using the invariance, and the invariants have simple expressions which are given here, and which corresponds to statistical quantities which characterize the flow. So in fact, we have something which is a framework which is mathematically consistent and which can be used in order to estimate the different coefficients. This was done for the channel flow, and so it shows it works. We can obtain the different coefficient beta and gamma. So beta and gamma, in fact, correspond to the coefficient on the T2 and T3 tensors. And so if we show beta and gamma, it's showed here. So they depend more or less as follows to the distance to the wall. But shown here for the annular flow, we can also see, and it's the same here, we see that they are diverging when we are very far from the flow. And also when the mean velocity is vanishing, the coefficients are diverging. So it means it shows that in fact this approach is consistent, it's working, but there is a problem because when the mean shear is going to 0, tensors T2 and T3 also go to 0, but R is not going to 0. And so we have coefficients which are diverging, and so it shows that in fact the framework is not adequate, it's not working. So this is, it was just simply to recall what has been obtained for the DNS case. And when we were speaking about the Kolmogorov law, I was interested to see if we can apply the same approach to the turbulent Kolmogorov law. So it's what has been done in the PhD thesis of Wenwei Wu. So this thesis was defended in last year, in February 2021. It was a co-tutela between France and China. And the advisors were myself, Enrico Calzaberini, and so Lipo Wang from Shanghai. And part of what I'm showing here is published in this paper of 2021 of Physics of Fluids. So about the turbulent Kolmogorov flow. So it's a flow which was proposed by Kolmogorov to his students in the late 50s. And the first known work about this, published work about this, is the one of 61, which is shown here. So it's an open turbulent flow. Sometimes it's called as a channel flow without boundaries. It's statistically non-homogeneous along one direction, which is seen here. And we have a forcing, which we call f of z, which is along the x direction, and f of z depends on the z variable. So we did some DNS of this flow using pseudo-spectral code, and we are making long integration time, and all the statistics are done over time and also spatially over x and y directions. And we consider two forcing. So one is the one originally proposed by Kolmogorov, because originally proposed a sinusoidal forcing. And another one, because in fact, this approach can be done even if the forcing is not sinusoidal, and we can make any kind of forcing for this. So we did, what we need is only that the average mean velocity is 0. So in fact, we choose the C quantity in order to have an average of 0. And using the parameters of the simulation, we can build a velocity scale and time scale, and so we can compute a Reynolds number. This was done for the sinusoidal case using 8 different neurons, so corresponding to different Reynolds numbers, which are shown in this table. So we have also different values of epsilon, R lambda, and etc. And so this was for the sinusoidal case, and for the Gaussian forcing, we did only one run. So the first result, we considered the mean and second moments. So in this plots, in dot line, it's the mean velocity, in order to have to see in which part of the flow we are, the different curves. And horizontally, it's a z. And here, this plot, we have the different second moments. And so first we see in the two cases, sinusoidal forcing and Gaussian forcing. And we see that, in fact, it's not it's the same as for the channel flow. It's not isotropic. It's because the different normal stress are quite different. And we have U prime square larger than W prime square larger than V prime square. So the smallest is in the homogeneity direction and the largest in the mean shift direction. And another important result, which is numerical, is the fact that U prime and tau, so the shear stress, are proportional. So it means that the eddy viscosity is a constant for this flow. So it's a surprising result. And if we use both results, so the first one, the first line is the first line of Navier-Stokes equation, and the second one is our numerical result. If we combine the two, we obtain the mean velocity, the shape of the mean velocity versus the forcing. And we see that the second derivative of the velocity is proportional to the forcing. The forcing f of z, we recall, is the one which is given here. So this was not found before, in fact, because for sinusoidal case, the second derivative is proportional to itself, so it's a special case, in fact. But for the general situation, it's what we checked here for the Gaussian forcing in this graph. We did twice integral of the forcing, and we obtained something which is completely superposed with the mean velocity. It's also interesting to see what is the shape of epsilon and k. So on the left, we have the sinusal forcing, it's run 7. We see that epsilon and k still have sinusoidal shape with a wavelength which is half of the forcing. But for the Kolmogorov with the Gaussian forcing, we have a shape which is unknown. We don't have the analytical expression for this curve. And also we see that k and epsilon, okay, they are similar, but still they're different because you can see that the maximum is not obtained in the same place, in the same location. So you cannot make a translation of one to obtain the other one, in fact. But we don't have the analytical expressions of these curves. And if we consider the eddy viscosity hypothesis, so we can consider the different tensors, and we can compute this indicator, all the coefficients and also the indicator. And what we see is that it's approximately valid when, because we have a ratio which is larger than 0.9 in the shear zone. So in the zone where the mean velocity shear is the largest. And when the mean velocity shear is small, then we have a failure of the hypothesis. So it's similar with what has been obtained for the channel flow. We can also consider a development, a quadratic development, and look at the other terms. This graph on the left seems a bit complicated, but in fact, it's very simple. The red curve is the alignment indicator with S. The blue curve is alignment with T2. The green one is alignment with T2, and the blue one alignment with T3. So we see that the green one is never very high. So we never have pure alignment with T2. And we see that when the red one is small, then the blue one takes the lead. And so showing that, in fact, in this special situations, there is alignment with T3. But if we consider the coefficients themselves, so it's good because we can have a quadratic development which is representative for the ensemble of the flow, except for shear regions where we still have this divergence problem. The coefficients are going to infinity in these different places. This means that, in fact, we have a non-zero value on the left. We have a constant coefficient here. T1 goes to 0. All the tensors, in fact, go to 0 in this place, and the coefficient beta and gamma needs to go to infinity. So it shows that it doesn't work. So to make comparisons, because the first one, which is surprising, the first comparison is to say that we found that eddy viscosity is independent of Z for the Kolmogorov flow, but for the channel flow, we can compute using classical database, and we see that, okay, it's approximately, for this Reynolds number, it's approximately constant, but not here, for the largest Reynolds number. And it clearly depends on the position. The two walls are shown here on the left and on the right. And it's a clear difference between the two flows. It doesn't work. So that was another difference is the fact that in fact we saw so here we have the sinusoidal forcing, the Gaussian forcing, and the channel flow. Here we don't have walls, but here we have the wall on the left and on the right. We see a shape which is similar between this situation and this one, but we see that in fact on the left for the Kolmogorov flow the plateau value is larger. We have a plateau which is close to 0.9. Showing that the hypothesis is approximately good in this place, but the channel flow, in fact, the plateau are much smaller, with a value of 0.5 or 0.6. And another similitude, another common point is the fact that, in fact, when as we already saw, that when the mean shear is vanishing, the hypothesis is not working. Here we have two situations, and here you have one here, and here you have one here, and also two close to the wall. We can also plot the indicator versus because we saw here that what is seems to be important is the value of the mean shear. So if we plot the value of the indicator versus the absolute value of the shear, we can see that we have shapes which have the same, more or less the same shapes. Something going from 0 to 4 small shears to the increasing, and they reach a largest value. And we have the same for the wall and the channel flow, but we have also this part of the curve which corresponds to the effect of the wall, in fact, for the channel flow. And we have also the failure of Boussinesq hypothesis close to the walls. And concerning the coefficients themselves, we see that they have also a common behavior, because coefficient in the framework of a quadratic development, we see that the coefficients are diverging also. In the two cases, we have a similar divergence. So a conclusion of this work is to say, as I said, that we have constant eddy viscosity for Kolmogorov flow, even when the forcing is not sinusoidal. And considering Boussinesq hypothesis, we found that the indicator works better for large shears, but the quadratic development can be proposed, and but this doesn't work when we have vanishing shears. And it means that, in fact, we need to perhaps to consider generalization of the constitutive equation that take into account memory effects and non-local expressions. And some works have already been proposed along these lines by considering viscoelastic analogies between the turbulence and viscoelastic flows. And for example, but in fact, we have also more recent proposal using such approach, but I think perhaps this one is one of the first that proposed to use an approach which has a memory effect with a kernel function here. And this would be perhaps a way to overcome the limitation of the quadratic development. That's all. And no, that's only if you have discussion, but that's all. Thank you.
Thank you very much, Francois, for the talk. So I would say let's open the question let's open the stage for discussion. Maybe there are some questions in the seminar room. You can let me know if someone.
Yes, we have one.
Yeah,
Okay.
it's me, Francesco.
Yeah.
So Thank you very much for this talk. I would like to ask you to detail a little bit more an aspect that I don't think that I got completely. When you use the Hamilton theorem to perform your expansion, I did not understand exactly how do you derive the coefficients of the expansion, beta, gamma, because this is kind of a hot topic right now. There are a number of papers, maybe in Sorbonne University, that are trying to determine these coefficients via machine learning. And I would like to see how you address this problem, the differences.
Yeah. In fact, it's something here that works mainly for this type of flow, because we have T1, T2, and T3 are orthogonal. So it's easier because you just make projections into the different bases, and then you obtain directly, in fact, the coefficients which are given here. So it's a projection. It's like in a product with a T2, T3, etc.
And this coefficient seem to tend to plus infinite in for when A tends to 0.
Yeah.
That? Okay.
This approach can also be done for general flows when we have more tensor bases, but I think they're not totally orthogonal with each other, so it's a bit more complex. But I think this approach, it was originally proposed in papers of Gatsky and Jongen and also perhaps Speciale, I think, at that time. And so they tried to make some projections. So it's a paper to obtain the coefficients.
Thank you very much.
Okay. Are there other questions in the seminar room?
Yes, there is one.
So you said that the hypothesis failed when there is no strong gradient. So on wall turbulence, for example, in channel flow, do you think that this is the main reason why the modeling with the business hypothesis failed, or it is because of on the region where it works that it doesn't work, let's say, perfectly? So because this is in the center of the channel that you have this failure, but do you think that it affects the full mean profile, this failure of the hypothesis in the center of the channel, or is it more due to what happened near the wall?
Yes. In fact, what was surprising is when we compare the two is to compare with Kolmogorov flow, where we have no wall effects, and for this it seems to work better for larger shears. So it could be seen as an effect of the wall, perhaps. Yeah. But yeah, it was surprising to see that it's almost working in some part of the Kolmogorov flow.
So basically, the regions with no shear, it's maybe not the main problem, let's say. Even if the hypothesis failed, it may be the main problem of the failure of using business hypothesis in this kind of flow.
For small shears, we clearly see that it cannot work because all the tensors are going to 0. In fact, ST2 and T3, and R is not going to 0. So there is clearly this representation cannot work, and we need to find something else.
So just a follow up on this point. So could you maybe comment on the idea of making an orthogonal projection? Because I suppose that this is actually the main point you were discussing before. I mean, it cannot work if we try to project R on an orthogonal basis of tensors. That's the problem, right? So we should go for a non-orthogonal basis. Is this the solution you are
not
proposing?
not precisely. It would be better to say that ST23 corresponds to local derivatives, and
Yes.
we should go to non-local properties, I think.
Yeah, but I mean, okay. Let me. I didn't express properly what I meant. Sorry. What I meant was, do you think that a local higher order representation of R would make sense? So instead of using only tensor operator, which are like local linearization of R, is it meaningful to include higher order local representations of R?
You mean without a linear development like here? So a kind of non-linear developments.
Yes.
Yeah, it's another way to see it. Yeah. I think there are different ways to try to generalize this.
Yeah, because in that case you would not end up with a basically. I mean, it's normal that when you have a shear that's 0, your linear approximation doesn't work, because in that case, I mean, you cannot define like the strain is the problematic part of your representation, right?
Yeah, because it's vanishing.
Yeah, exactly. But in that case, it's like saying that the Jacobian of your velocity is vanishing, but then you can take the second order, differential operator of your velocity, which is not supposed to vanish. No. Okay. Okay, so are there other questions in the room?
Not for now.
Not that you see it?
There is one.
Oh, go ahead.
For this slide, for the radial stress tensors, strictly speaking, that we have the degree of freedom of this stress is 6, right? And so, strictly speaking, that we need at least a 6 tensor base to remodeling this radial stress tensor. But why here you have just 3 tensors for?
Yeah, there are 3 because it's a more simple case with which is the wall flow. So it was developed for such. But inside, I don't know exactly. But if we go back to, I don't know, looks here. The work of Pope, he said he proposed here that we need a 10. I believe that the 10 are not totally independent. That's why it's a maximum of 10. I believe. I don't remember exactly how we derived this. The fact that we have 10, of course, because if we listen to what you just said, there is more than too much, in fact, in the development. And I think, but it's in all the theoretical works that have been done at that time, I think they discuss all this and they try to see which basis should be removed. I think that it's a kind of redundancy. I agree.
I was concerned that why you choose T2 and T3, but not T10 or T8, for example.
That was shown in some of the work. That's in fact for channel flows when you depend only on one quantity which is variable. Many of them are vanishing. So in fact, you only have to go to the second order. I think it's the book of Pope is discussing this, perhaps.
Yeah.
Concerning the number 10, I would have defined utility a tensor
So R equals tensor times the tensor. And there's always a tensor like this. That would be 9 rather than 10.
Yeah, there's some development where, in fact, art is tried to be developed as a higher order tensor with eddy viscosity, which is also a tensor in itself. Yeah, so there are also some works about this, but I think for modeling applications, it's really too complicated.
About the memory effect, actually, how this should work, or how it should solve part of the problem.
The memory, yeah, the memory is a way to take into account the fact that, in fact, because if we have an expression using quantities which are vanishing, it won't work because it's local derivatives. So here the derivative, we are not considering only the local derivative, but also derivative at other places. So when we are in places when the shear is vanishing, there are contributions from places where, in fact, the shear is not vanishing. So it's a non-local effect. That's a way to overcome.
So it's basically quite similar to look at the shear at higher scale, let's say. Then not to look at the shear at the
yes,
locally, but to
yeah,
see a bigger scale what is the shear.
Yeah, it would be another way to express it.
But here the integral is on time.
Yeah, that was the proposal of INS, but in fact you can transfer time into space.
Okay, thank you. So is there someone else who would like to ask a question in the room?
No more in the room.
No,
now.
doesn't seem to be the case. So maybe we can see if we can give the chance to someone else from part two to ask a question. Just feel free to unmute your mic if you want to ask a question. Let's see if there is someone who would like to ask a question. And it doesn't seem to be the case. I do have one question. Maybe it's on the same line of what we were discussing, what it was discussed before with the Reynolds stress tensor. You know that recently, I mean, they become more and more popular in recent years. There are models that actually include one model per each term of the Reynolds stress tensor rather than using the Boussinesq hypothesis, right? And I always read the argument, okay, they are too expensive, and that's why Boussinesq hypothesis is more popular for commercial softwares or for industry because it gives rise to a less expensive model. Is it still the case that Reynolds stress tensor models, like for each term of the Reynolds stress, are less expensive if compared to this kind of tensorial development of the Boussinesq hypothesis, or they are comparable, or they become comparable in terms of computational cost?
You mean computation cost between the full Reynolds stress models and nonlinear eddy viscosity models?
Yes.
I think full Reynolds stress is still more cost, but now that we have powerful computers, it could be tried. But I don't know of any application of this kind of models outside outside the experimental situations. So I mean in the ocean or atmosphere, full scale in the environmental applications, always people are applying very simple models.
Yeah, Yeah, sure. But
I find too bad because it's really bad models. So
yeah. Actually, there are like benchmarks in flow in a duct that's very classical, in which Boussinesq hypothesis fails to predict the secondary flow, like at the corners, and when you include like either nonlinear approach or Reynolds stress tensors, they do manage to capture what is observed as a major feature of the duct flow in the experiment. So yeah, I don't know. I don't know if this kind of approach can. I think they do actually perform well also in a duct. The approach you just showed, right? Duct flow.
yeah.
Okay. So if there are no other questions
There is one more last.
There is one? Okay, cool.
Yeah. Last question.
Go ahead.
I wonder whether it would be enough to include the memory effect to resolve the problem, because actually the Reynolds stress appears in the Reynolds equations as a gradient of the Reynolds stress, the derivative, which turns out to be really the average of the velocity plus the vorticity. So we are talking about the correlation between the velocity and the vorticity. So the correlation between large scales and small scales, which even at very high Reynolds number, is present. And that is really what we need to find a way to model. It's very difficult.
Yeah, it's more common than. Yeah, but I agree. Yeah.
That's what I say, my last
Yeah.
one.
Yes.
Yeah, but I mean, just a comment on like maybe I didn't hear very clearly everything, but I think that already for the case of the Kolmogorov flow, where the mean flow doesn't change, that memory effect would not play such a major role, because the mean flow shear, it's still gonna be zero, right? Where you have a problematic entry of your model, right?
Yeah, the comment was about the limitation of the memory effect.
Okay.
That Reynolds stress development with a memory effect would not be enough to solve the problem.
Okay. So we are on the same line. Okay, fine. Good. So thank you very much, Francois, for the talk and the nice discussion which emerged afterwards. And I invite all the participants to thank you. And I think we can conclude here the seminar, if you agree.
Okay, thanks.
Thank you very much. Have a good evening to everyone.
Yeah.
Bye.
Bye.